Mentioned earlier, there are ways we can measure and forecast wind shear. One of the most popular ways to examine wind shear is on a hodograph. In this example, we see an increase in wind speed with height, as denoted by the 10 knots of flow as indicated with this single barb, upwards of 60 knots of flow as indicated by the flag and the individual barb here on this staff. Now, these wind barbs and flags are all oriented in the same direction, and this indicates that we don't have much in the way of a wind direction change with height. And then when we take these individual points along the wind staff and plot them in a 2D plane, as we see here, we see that the resultant line is straight, and that's where we get the term a straight hodograph. The gist of a straight hodograph is that it is very important, or it signifies an environment that is conducive for splitting supercells. So conceptually, in this environment, an individual storm cell may develop, as we see here on the left, provided that there is a sufficient amount of deep layer wind shear. Again, remember, typically the number that we're looking for when we're diagnosing whether or not we have an environment conducive for supercells or not is 35 knots. So in this case, we more than likely have greater than 35 knots as indicated by our wind staff. And this initial supercell type storm that typically, or will typically have one updraft, may eventually split into two. And in a straight hodograph environment where we have splitting supercells, one storm cell will rotate anticyclonically or clockwise, while the other storm cell will rotate cyclonically or counterclockwise. More importantly, in a straight hodograph environment, both of these counter-rotating pair of updrafts, the storms themselves will split and have an equal chance of persisting after their split.
Visually, splitting supercells may be difficult to observe. However, Daryl Hersman from the Iowa State University has an awesome time-lapse that shows a splitting supercell. Note, toward the end of the time-lapse, how the updraft towers appear to be diverging and moving in different directions. Here is a radar example of splitting supercells across North Texas. During the initial loop, you hopefully noticed the splitting cell between Kaufman and Terrell. The cell that moves more northeastward into northern Kaufman and southern Hunt counties exhibits high reflectivity values indicative of large hail. As is usually the case, these left split or left moving supercells tend to produce large to giant hail. Giant hail is defined as hailstones 3 inches in diameter or greater. Damaging winds and tornadoes are less common with the left-moving supercell, but they have been documented to occur. The right split, or right-moving supercell, tracks through southern portions of Kaufman County. The right mover has a higher probability of producing multiple hazards, including large hail, damaging straight-line winds, flash flooding, and tornadoes. In this instance, the right-moving supercell across southern Kaufman County produced a tornado near the city of Maybank.
Next, let's examine what happens when we have an environment that is characterized by both speed and directional wind shear. In this idealized wind profile that you see on the left, we notice that not only do the winds increase with height, but they also change direction as well. When we plot the winds in a 2D plane, we get more of a curved hodograph. Typically, across North and Central Texas, the hodograph curves to the right or in a clockwise type fashion. Now, if we do get splitting supercells in this type of environment, typically the right-moving supercell will be favored. On the other hand, the left-moving supercell is typically not favored and will often diminish and weaken sooner than its right-moving counterpart. Here's a radar animation that shows an environment characterized by a sharply curved hodograph in which the right-moving supercells are favored. We'll go through this radar animation in greater detail in the coming slides. To continue to talk about the right mover, in this animated GIF, we notice a very interesting trajectory of the supercell near the city of Mineral Wells. Now, as the animation plays, note the behavior of the reflectivity associated with the hook echo that initially moves to the northeast toward Springtown. It diminishes rather quickly. The larger core to the south, however, persists as the animation restarts and moves through the Weatherford and then even close to the Aledo areas. We can see that this storm has deviated pretty sharply to the right, and that's a direct result of the strongly veered wind profile with height promoting healthy mid-level rotation. This mid-level rotation is the driver of deviant storm motion, and in this case, the storm dove sharply to the southeast toward Crescent. The storm north of Stephenville also exhibits a sharp deviation to the right. Take a look at the crude composite and notice how the center of the storm cell shifts toward the southeast in time. If you're around on this day, you know that several tornadoes occurred, including a very noteworthy tornado near the city of Granbury in Hood County. It is important to have the ability to anticipate storm motion and behavior when storm spotting. Across north and central Texas, an environment that exhibits mostly wind shear with little to no directional shear will favor splitting supercells. In these straight hodograph environments, both the left and right mover will have equal chances of sustaining themselves. And be sure that you review the hazards associated with both. In general, the left mover in these straight hodograph environments will typically pose a large to giant hail threat, though the tornado and damaging wind threat are non-zero. The right mover in straight hodograph environments will have the potential to produce large hail and will have the greater damaging wind, flash flood, and tornado threats. And as highlighted here, when dealing with an environment that is cyclonically curved, or it exhibits a cyclonically curved hodograph, typically the right mover will be favored, and this right mover can and does deviate oftentimes to the south and southeast. Now that we've explored supercell motion, now is a good time to discuss some of the important downdraft characteristics of a supercell. Let's begin with our basic schematic of a classic supercell. Note the kidney bean type appearance with a hook echo type feature. We will assume a storm motion from the bottom left of the screen to the top right portion of the screen, and in general, a southwest to northeast motion. Next, we will break the supercell into 4 quadrants or flanks. We will spend the most time talking about the forward flank and the rear flank. The hook echo is a direct result of a mesocyclone that develops near the interface of the rear and right flanks. Because this region is characterized by relatively lower pressure, warm and moist air has a tendency to flow toward the inflow region. And this is what we call the action area. If a tornado is to develop, it's most likely going to happen here. As the air descends from the rear flank downdraft, or RFD, and is pulled around from the rear flank, we oftentimes see the potential for tornadogenesis to increase. It is often cooler and denser than the inflow, and thus has a tendency to rush toward the right flank. There is a contrast between the relatively cooler air from the RFD and warmer, moist air in the inflow region. Sometimes this warmer and more moist air is forced upward, and a line of cumulus clouds may develop along the RFD gust front. Sometimes this cumulus can grow into additional cumulonimbus and help sustain the supercell as it propagates through the atmosphere. Now, closer to the forward flank, air here is oftentimes rain and or precipitation cooled. Like the RFD, this air typically is of greater density and also has a tendency to accelerate toward the ground and spread out. This creates another temperature gradient along the forward flank and right flank and can give birth to a forward flank gust front. Both the RFD and FFD gust fronts can be important to the sustenance of the supercell. If the temperature associated with the RFD and FFD are sufficiently lower, cooler and more stable air can cut off the warm, moist inflow winds into the mesocyclone, resulting in the storm's demise. Conversely, if the air from the RFD and or FFD are sufficiently warm, then a balance can be achieved that would promote both the maintenance of the supercell and potentially promote tornadogenesis. We've gone through a conceptual model of supercell downdrafts. Let's examine what this looks like on radar. The image here on the left shows the radar reflectivity, while the image here on the right denotes the base radial velocity. Now, in this imagery, the radar is located to the left in each panel, or more than likely to the west of the target. The greater reflectivity, or red and pink areas seen here, indicate the forward flank downdraft, with a noticeable hook echo down to the south and west. Now we have relatively lower reflectivity values here along the RFD gust front, and more than likely this gust front is actually kicking up biological flyers, as well as the potential for generating a few more updrafts along the flanking line. We do see the corresponding base radial velocity imagery here on the right indicate flow away from the radar associated with the RFD. Note the higher inbounds here in the right image, just to the right of the greatest outbounds, or to the east of the greatest outbounds. This is likely our warm, moist inflow air. Notice how the velocity values co-located within the greater reflectivity values occur in the forward flank downdraft. While not as great in terms of magnitudes of winds as those values or the inferred velocity as seen here in the warm, moist inflow, there is a slightly more smoother appearance to the base radial velocity here. And this is more likely due to the fact that there is more stable air associated with the precipitation, mainly rain and hail. Note that this smooth velocity transitions to a more granular velocity field, and it's likely here at this interface between very smooth looking velocity and a lot more granular velocity that we have our forward flank gust front. What might the visual of the FFD, or forward flank downdraft, be if one was positioned correctly? Here's one possible perspective of a spotter looking back toward the forward flank region. Notice the precipitation shaft with the sheet-like appearance, and then note the choppy underbelly of the shelf cloud. Recall from the basic presentation, a visual sign of outflow is the appearance of turbulent-looking clouds that slope down and away from the precipitation core. The leading edge of this precipitation cascade is often demarcated by a shelf cloud. Now, depending on the storm's motion, there's a chance that this spotter may have needed to reposition in order to avoid being impacted directly by the core itself. Next, we will shift gears to the rear flank. Similar to the forward flank, we note the outflow stratus in the form of a shelf cloud with a precipitation core in its wake. From this perspective, however, the spotter is also able to visually capture a region of inflow. Note the smoother, more laminar-looking cloud structures in the inflow area and compare that to the more turbulent-looking clouds along and in the wake of the shelf cloud. In the inflow area, one can also observe the tail and wall clouds, which are again inflow clouds. Here is an example of an inflow region. Typically, the inflow region will not have any precipitation. However, in some instances, inflow may be sufficiently strong enough such that dirt, dust, or bugs are kicked up. Recall from previous SKYWARN presentations, you know you're in a region of inflow if you're looking at the storm and the air pierces you through your back. Now, regions of inflow are also characterized as relatively moist and warm. An additional sign of inflow is if you notice vegetation bending or blowing toward the storm. What else do you see in this picture that might be a sign of inflow? Perhaps you notice the beaver tail. This is a sign of inflow toward the storm. Now, beneath the rain-free base, oftentimes we often see a triple point or a conversion of various air masses coming together. We'll talk about the significance of the triple point in the next few slides. Let's examine that triple point from a radar perspective. And we've seen this imagery before, but let's annotate it a little more. Remember, locate the radar when interpreting Doppler radial velocity. And in this instance, it's toward the center of the screen or near the white dot. Green or cool colors represent flow toward the radar, while red or warmer colors indicate airflow moving away from the radar. Now, in this example, we have a rotational velocity couplet suggesting a high tornado potential. Note the broad inbounds along the backside of the couplet, and this is more than likely associated with winds coming from the rear flank downdraft or the RFD. Note how this kind of butts up against airflow away from the radar or in the inflow region here. At this interface, it's likely that we have the RFD gust front. And remember that RFD gust front will separate the cooler and sometimes drier air associated with the RFD from the warmer and more moist air associated with the inflow region. Now, if we pan back to the top of the screen, we see a modest area of inbounds likely associated with the precipitation cooled air of the forward flank downdraft butting up against the warm, moist inflow air. If we examine what this looks like visually, with the observer looking back toward the north and west, presuming that up is north, we can see toward the interface of these converging air masses, the warm, moist inflow air, the forward flank downdraft air, and then the RFD air. At this interface, we have the development of a tornado. Now, the gust front, as seen here, is likely demarcated by the outflow stratus and the RFD shelf cloud seen here in the image. Note that the location of the wall cloud and tornado likely along the warm portion of the RFD gust front, again, in this pseudo triple point area.